Hi, I'm Dr. Asegun Henry. I'm a professor at MIT, and from where I sit, climate change is the most important problem in the history of mankind. And that's because it's one of the most imminent threats to our survival as a species on this planet. So in order to solve this problem, we basically have to do a complete overhaul of our entire energy infrastructure, switching from fossil fuels to renewables. Now, what's amazing is that the price of solar and wind has dropped dramatically over the last 2 decades. The problem is that you don't get the electricity when you want it, and the plot on the left shows that this produces a dramatic shift in the load. The problem is that big ramp in power production that has to happen when the sun goes down, which cannot be met by fossil fuel turbines. As the plot on the right shows, the fact that renewables can't provide power on demand limits how much of the grid's energy they can provide. So if we don't have storage, we can't have more than about 20% of the grid's energy supplied by renewables, because we're forced to throw the rest of it away. So energy storage is the key. So the first question people usually ask is, okay, why not just use lithium-ion batteries? And the answer is simple: they cost too much. Now, a number of independent studies have looked at what it will take to decarbonize the grid, and they've all come to the same conclusions shown on the bottom left. Number one, surprisingly, efficiency is actually not all that critical. As long as you're above about 35% efficiency, you can make money. So it's useful to sacrifice efficiency if it buys you lower cost per unit energy, or CPE. Number two, CPE is by far the most important parameter, which is why the colors change the most in the horizontal direction on the figure on the right. And in order for renewables with storage to displace fossil fuels fully, we have to get to the blue region, the part that's darker than the natural gas dark blue indicated in the legend. Therefore, number three, in order to go fully renewable across the nation, all the studies listed at the bottom have concluded that we need a technology with a CPE less than $20 a kilowatt hour. So that's what we need in order to save our species from extinction. So the next question is, what options do we have? Lithium-ion batteries are at about $150 a kilowatt hour now. They are slated to maybe get down to $50 a kilowatt hour, but still, that's too expensive, because what we need is less than 20. Pumped hydro's at about 60, but it's geographically limited. It's hard to site, no new plants are being built. And sometimes people like to throw compressed air energy storage in the discussion because it's down around 30, but the existing plants all burn natural gas, so it doesn't solve our CO2 problem. So what else is there? Well, what we're developing in my lab is a radically different approach. Since efficiency isn't the main thing that matters, we can get super low cost by storing heat instead of storing electricity directly. So the way the system works is we take in electricity and we run resistance heaters that are basically giant incandescent light bulb filaments at 2500 degrees Celsius, which is glowing white hot. We then heat up the liquid metal tin to 2400 degrees C and pump it over to a giant storage unit filled with cheap blocks of graphite. And we pump the tin through the blocks to heat them up to 2400 degrees C. This is how we charge up our thermal battery. Then, whenever you want electricity back, we pump the liquid tin back through the blocks to remove the heat and carry it over to the power conversion unit. Now, what's different here is normally you'd use a turbine to convert heat to electricity, but here the reason we jack the temperature up so high is because we want to instead do the conversion using photovoltaics. And these are not normal solar cells. They're specially designed solar cells that have a highly reflective mirror on the back, so that any of the below band gap light that's not converted in the cells gets reflected back to the hot piping infrastructure, thereby preserving the energy so it's not wasted. As the tin flows through, it cools, its heat gets converted, and then it's routed back to the hot graphite blocks to be reheated, and this is how we discharge the thermal battery. So after hearing all that, I imagine you got lots of questions, so I'll try to quickly address two of the biggest ones. First is, how much does it cost? And the short answer is our cost estimates for the full system come to less than $10 a kilowatt hour. That's more than 10 times cheaper than lithium-ion batteries and half as much as what the analyses say we need in order to save the species. The second question is, what should come to mind after some crazy guy says we're going to pump liquid metal above 2000 degrees C is, how are you going to pump it? And this is the technological breakthrough that started all of this. About 4 years ago, we figured out how to pump liquid metal using all ceramic or graphite mechanical pumps and seals, and we have a paper in Nature describing the first instance where we pumped at 1400 degrees C, which is in the Guinness Book of World Records. More recently, we've pumped above 2000 degrees C, so the idea of building an all graphite infrastructure to pump liquid metal, all held in an inert environment, is now possible. So lastly, I'll quickly mention what we've done and where we're headed. So we've demonstrated the pumping, we've demonstrated the materials work, we've demonstrated high efficiency thermal photovoltaic cells via our collaborators at NREL. We recently set a new world record for efficiency above 40%. We've built and tested each component separately, and so the remaining steps are to demonstrate the full system as a lab scale prototype over the next year, and then I'll have a startup looking to raise money for a pilot demonstration at a 1 megawatt hour level. And if everything goes well with that, then we'll be looking to scale up and get this technology deployed as fast as possible in hopes that we can mitigate climate change fast enough to save our species from potential extinction.